Welcome. All right.
Thank you.
So yeah, perfect. We see your screen. It's working well. So thank you for being with us, even virtually. So we're going to hear Hadi Daneshmand from the University of Virginia. Who's going to discuss understanding test time compute. Please go ahead. Thanks.
So thank you so much for your invitation. It's a great pleasure to be here. So sorry if I couldn't join in person. So today I want to talk about test time compute in large language model. And I am at University of Virginia. I just joined 6 months ago as a new assistant professor. So just before starting the talk, I know this is a hybrid, kind of hybrid, kind of in-person and remote event. So I request to prompt me for question during the talk. I know that is a little bit difficult, maybe challenging because I am remote, you are in person. So one way to do it is basically, I think the best way to do it should just go to the speaker mic and just ask your question. I think that's the best way because then I can hear you using the mic that is in front. So this is the outline of the talk. What I want to emphasize is that this talk has this structure that is start from something more general overview, and it goes deeper and deeper and become more technical during the talk. So the reason that I'm mentioning this because is that it's important first to understand what is happening at the beginning. It's better to ask your question earlier. The other reason is that if you ask so many questions and you couldn't continue, you just miss the technical part of the talk. So I hope this encourages you to ask questions during the talk. So can you hear me well? Is it clear?
It's very clear. Yeah.
Okay, perfect. So I want to just test the kind of communication approach and motivate the talk with one question from audience. Suppose that you want to use ChatGPT to swap character in sentences, okay? The first and third character or something. So we can code to solve this task, but the question is that how we can use ChatGPT to do that. So maybe if you use ChatGPT a lot for your research or for your exercises, you know how to prompt it properly. So can we somehow communicate and have a few ideas about how to solve this task?
We have no idea. Go ahead.
Okay. So this is the prompt that straightforward. You can say, okay, let's just swap the first and third character. Sorry, this is the prompt that I give to the ChatGPT. And what happens is ChatGPT do this kind of what is called chain of prompting is try to locate where is the first character, where is the third character, and try to swap it. And eventually it make a mistake. So it doesn't swap, it just replaces the first character. So how we can solve it? One solution to solve to this problem is something that is known as in-context learning. Sometimes people call it also few-shot learning. So you can provide example of swapping character to the language model prompt, let's say ACCA, QMMQ. Here I swap the first and second character in very simple word, just to present it in the better way. And after showing this language model a few examples of the swapping character, it can learn and extrapolate and swap the character in the new word. So what is happening here is that if you provide a good context to the language model, it can solve the tasks. Why is surprising? Because ChatGPT is not trained for this particular task, and it's very powerful. You can prompt the language model, you can give example at the test time to the language model and expect to solve new tasks at the test time. So it's introduced a lot of adaptivity that doesn't exist in traditional machine learning models. So the other example that you can consider is, maybe you use this deep search component in ChatGPT, that if you ask a question, you see that the ChatGPT solve it through step-by-step action. So, and read a blog, a paper, and so on, to generate kind of good output. So what is the difference between test time compute and training time compute? Is completely different. So most of the machine learning focus in last last 2 decades was about training time compute. So you have a model that you could change its parameters. You have a fixed data distribution, and you have a task like image classification that was fixed. At the test time, you wanted to do the same thing, right? So the data distribution, from empirical distribution in the best case, in the worst case, you wanted to just test on the same distribution, but not empirical version, but there was no kind of significant shift in the distribution. The task was the same, image classification, and you had the option to change the model parameters. So at the test time, the models are fixed. So what you change is the input to the model. So the data distribution may completely change, like swapping character. I can give any kind of character or any kind of sentences to the model. And the task is completely different. So the question is, what I want to stress here is that the test of compute is very, very kind of important in industry. If you just review the recent technical report of OpenAI, Google Brain, and DeepSeek, you will see there is a strong focus on test time learning. So here is one example of the technical report of OpenAI, is online available, about how they develop all family of ChatGPT. And there is a very nice plot, a nice comparison that they provide. So if you invest on the test training time, let's say you give a larger data set to the language model, you increase the size of the model a lot, you can improve the accuracy. But there is another way to do the same thing, is that you just focus on the way that you prompt the model at the test time, and your performance can get much better as well. So, and there is a lot of practices and a lot of methods that developed and are tuned to the test time and compute. One of the, for example, in the trustworthy application, there are methods for unlearning harmful content in language model. Suppose that you have this mixture of two kind of distribution, that are trained and accidentally given to the ChatGPT, and you want surgically to remove one of the modes. So how to do it? One way is to prompt the language model in the correct way. So the other, let's say, growing practices in language model or reinforcement learning based prompting. So the way that they work is that you basically generate the output given the prompt, and you evaluate the output and change the prompt according to the feedback you get from the model, and you continue doing this to improve the quality of generated text. So what I want to talk about is about how to understand this technique. So this is the goal I have, and I will go through a few kind of recent results that we had about the test time learning. So before continuing, I want to pause here to ask if you have any question. I will be glad to address.
I think it's very clear.
Okay,
Yes,
thank you. So why test of time compute is difficult to study? So let's consider one simple example. You want to prompt the language model to sort the list, okay, at the test time. The first thing that happening is that the length of this list is not fixed, okay? So we cannot basically say we want to just sort list of length 4. Maybe because the language model can accept, or by design they can accept input of different length because the sentences are different length. The length of the list can be arbitrary. The distribution can be arbitrary too. We cannot, using this classical setting of machine learning, when we assume that the data are IID from some distribution and do average case analysis. We want to have a kind of worst case analysis at the test time. So this is a very difficult and challenging setting to study. So the question is how to simplify, and one of the simplification that recently is becoming much more popular is proposed by Garg and co-authors in 2022. So they suggest to study in context learning of regression. So let's start from fundamental problem of regression that we know a lot about and see how language models solve it at the test time. So at the test time, you prompt the language model. I know that is a bit confusing here because the language model, we do usually the test prompting, but here the xi and yi in for regression, they are vectors. So the idea is that, okay, so you have one step of doing word embedding in language model, but eventually everything turns to the vectors. So you can put basically vectors in the input of the language model and see how it solves the regression problem. So the interesting thing that what we want to study how the behavior change at the test time. And what we do is that we train the language model at the using for this particular task of linear regression to understand what is happening at the test time. So how we can train it? So the way that people suggest to train is to draw random samples, generative data, let's say xi's are some vector, Gaussian vectors, multivariate normal variables, and then you draw a random direction, let's call it W, and you project the xi on the W to generate a set of constructive example to train the model. So then the goal of this kind of training is to predict the label associated with the new sample xn plus 1. Okay? You want the model to solve a regression task on the training data, but at the test time, this W vector will change, and the data distribution can change, can be non-Gaussian, can be just atomic, has one atom on particular data points. So what is shocking is that after you train this model, okay, you can change the number of examples that provide for regression in the prompt, and the model, the performance doesn't get worse, it gets better, okay? So the distribution at the test time can be significantly different when you change the number of samples, right? The support of the distribution is changed, is more higher dimension, but the performance of the model doesn't get worse, gets much better. And it can, do as well as linear regression. So it sounds that the model is not trying to overfit to the training, not only trying to overfit, but also is actually using the in-context example to do performance, because when you provide more examples, the performance gets better and better at the test time. So we studied this, and what I call it, what is happening, I want to just quickly mention what happened in this kind of shocking observation. So what we observe is that gradient descent emerged after running gradient descent. So let's say you run gradient descent to optimize the training loss. So we know that the gradient descent, if the function that you optimize is sufficiently smooth, converge to the critical point, right? So what we proved is that there is a critical point of this training objective that implements gradient descent on the in-context example, on the task of linear regression. So there are two different optimization happening here. I call it twofold optimization. One fold is the traditional optimization that we study a lot. Is you have a training dynamic, you have parameters, you optimize them. And after you optimize it, the training has different attractors. Some of them are stable, some of them are not. And one of these attractors, if you plug in it to the parameters of this attention layer, across the layers, you see the feature dynamic is implementing some algorithm like gradient descent. What I need to stress here is that the feature dynamic doesn't have access to the parameter vector, so it doesn't see the parameters. The only things that is updating across the layers are actually data representation. And so it's very hidden dynamics. So it's not a kind of one-to-one map. You have to explore how the data distribution change and how we can interpret it as a gradient descent. So what I want to basically stress here is that there are these two different optimization actually have a kind of interplay, have basically influenced each other. So you can, with using different data distribution for training, Gaussian with different covariance matrix and so on, you can encourage the feature dynamic to learn encourage the feature dynamic to learn preconditioning and regularization. So what I want to stress here is that the model just train on random data, okay? So a bunch of data you throw and a bunch of linear regression you show to the model. The model can learn from this data to implement algorithm that we develop over years of research. It can learn to do preconditioning and regularization just by observing the data. This is quite non-trivial because the model, didn't want, it could solve this task differently. It could just memorize the training data. So I want to talk about two limitations of this work. Also is significant. It has two main kind of limitation. One is that most of the in-context learning theoretical research is focused on linear regression task, which is interesting, is a good start, but may not be directly related to kind of generative AI goal. So the other important limitation is that the model is simplified. So the transformer and language model have components that call attentions. But in this research, usually we use a simplified model of attention. So I want to just introduce a little bit what is attention layer here, which is quite significant component of language model, is good to know. And what is linear attention, that is simplified attention used in context learning research. So the attention takes a matrix written another matrix. So I use the V1 to Vn to highlight the rows of this matrix, and Vi plus to denote the kind of rows after passing through the attention. And it has two parameters, two matrices, let's say. It has more than two, but this is a kind of abstraction. So these are two matrices of proper size. And the way that attention works is combines the inputs. So move each rows along the matrix multiplication by linear combination of these vectors. And the weights that you use in this linear combination depends on the inner product of the VJs, the vector input rows itself. So the original attention used this kind of weights, which known to be a kind of soft max. It's differentiable version of the maximum, and the linear attention just use the linear. So why we call it linear is not linear in the input, but is linear in its parameters. So I want to just pause here a little bit for question, and at the same time, just if you don't have question, you can think about this problem. How to, so suppose that you have attention, how we can represent this difference using linear transformation of gradient of a convex function. So what I want to say here is that the attention by construction is a gradient function, which motivate what I will talk about later. So please go ahead if you have question about the current topics that we discuss. I will be more than glad to answer.
So you said before that that in context learning learns precondition gradient descent. Could you say something about why precondition gradient descent and not any other type of regularization or second order method or something else? So what's special about preconditioning?
So this is a very good question. Why it learns to do preconditioning? So I would say this depends on the. So depends on the. First of all, this is really tied to the model that you use. So what we have a bunch of different model that we consider. So in some of the model, we impose kind of a sparsity constraint on the weight matrices, and that leads to the emergence of preconditioning. And if the, for example, input, the context that you use has a small size, the model learns to do regularization. The regularization factor vanishes with the number of samples that you provide in the training time. So it depends on the training and the model that you use. So what we did in this paper also, we lifted the sparsity condition to see whether the model can learn more complicated algorithm. And the answer is yes, it can learn complicated methods. So with better, we think the convergence rate is better. So we basically have this formulation of the algorithm, but we don't know the exact convergence rate. So it can learn a more complicated method. We basically think is a kind of second order method, but is not trivial second order method that we use because they implement, as I said, is that they are updating the data representation. So sometimes it's difficult to connect this kind of iterative process to the well-known algorithm. So there are some algorithms that are implemented and we don't have any clue about them. The preconditioning and regularization are the algorithm we found and we can interpret. So yeah, about your question that they can learn more complicated second order method, yes, even linear attention layers can do that. But I talked about the algorithm that we have interpretation for them and convergence and everything. And if you are interested about which kind of other algorithm they can learn, in the last theorem that we provide in this paper is about one algorithm that even for which we don't have a convergence rate. It's called GD++ in the literature.
Thanks.
You're welcome.
There's one more.
Thanks. So I was wondering, so you're claiming that transformer can do gradient descent in context, but so it's clear that in this case, it's doing gradient descent like parameterized by shallow linear network or just linear regression, and you train like the W, the linear map. But what about like it learns something else? It's like binary classification or some other nonlinear functions. Then what does gradient descent mean, right? You need to first parameterize the model and then do gradient descent on those parameters, right?
Yes, this is a very good question. Thank you so much. So the question is that what if I change the task, from the linear regression to classification? So there are research about that. That is, I haven't went through the details, but for example, there is a paper talks about implementing SVM with transformers. And they basically have this intuition that the kind of transformer can implement SVM across the layers. So these are the, I didn't study the more complicated cases. So, but there are ongoing research to do that. So for example, one other top task that people study is about kernel regression. And basically, if you use softmax attention not softmax attention, exponential attention. So if you basically replace let's see, where is the attention? Replace this softmax, remove the denominator, then the transformer can do a kind of particular kernel regression for solving linear kernel regression. So there is an ongoing kind of research about how transformers solve classic tasks that we know how to solve. So always the network doesn't find the parameters that we usually kind of use to optimize the model. Sometimes the behavior is quite different. And one of the, even for linear regression, we observe sometimes it's difficult to interpret what they are exactly doing. But what is interesting is that if you assess the performance across the layers of transformer, it sounds they are doing it iteratively. So the performance gets better and better when you add more and more layers. So this inspired that they are doing a kind of iterative optimization method across the layers.
Very, very interesting. Thank you.
Thank you for your question.
So I see no more questions, so you can resume. Thanks.
Thank you for your questions. Yeah, this question, so if I wanted to just answer people who had time and think about the puzzle. So if you want to rewrite this quantity, you can write it as a gradient of this function times Q inverse. This convex combination of the vectors is actually a gradient operation times the matrix. And this inspired that, okay, so the attention is the gradient of even a convex function. This is also important to know. Maybe we can use it as a kind of computational unit. So we can use the attention to implement one step of gradient of some convex function and iteratively solve different optimization problems. So there are two other results. There was this question that, okay, so linear regression, maybe it's too simple. What we can do for different tasks. So I studied two other tasks. So one of them is reinforcement learning. So why reinforcement learning? Because the test time compute has a strong focus on reinforcement learning. And our question is whether the transformer itself can do reinforcement learning at the test time. So if you want to know more about it, so the observation is that the transformer learn a known algorithm called temporal difference to compute the value function. So this result that is quite recent, and I will refer you to this paper if you want to know more about it. What I want to talk about is more about optimal transport and sorting. So let's say if you are not familiar with optimal transport, but all of us knows about sorting, is that how transformer can sort lists at the test time, when the length can change, when the parameter, the distribution can change, and so on. And I want to show how transformer can implement a gradient, a kind of gradient descent to solve this task. So the rest of the talk I focus on the optimal transport. The question that you may ask, okay, why optimal transport? So why transport between distributions? So the generative model and generative AI goal is, the method that we have, mostly based on transporting a simple distribution to the complex distribution. Let's say in the diffusion model, you want to have an image that is completely noisy and it has II Gaussian elements, and you want to apply a nonlinear transformation on this image and get, let's say, this question mark image. So this is, I think, more closer to the generative AI, not exactly the kind of generating text. And the particular task that I want to study is optimal transport for discrete measure, which is simpler to analyze. So I picked this example from Marco Cotturi talks. It's very nice example. That so to introduce this problem, the discrete optimal transport. Suppose you have a bunch of points, and then we turn off the light. You cannot see the points, and then you change the position of these points or updated. The question is that who moved to where? So what you have position at the beginning and at the end of this process, but you don't know who, you don't know any matching between the points, and you want to find this matching. So you can formulate this problem mathematically. So you have a set of point xi's that basically shows the position, initial position of the points, and yi's that shows the position of the points after the moving. And what you can introduce is a kind of integer program that to find the optimum solution, optimum matching between points after and before moving. So this integer program is the problem of optimization and matching between xi and yj's, which is a permutation matrix. So that's why we have integer program, because the elements are 0 and 1. And the way that you want to prompt the language model at the test time to solve this task, you give the points in the prompt, and you ask the language model to predict the solution, okay? So the question is that whether the language model can do this, solve this task or not, this integer program. And what I want to tell you is that, so what we can do for this task is that we can generate a similar IIT Gaussian data and learn the model on this constructive example and see what happens at the test time. So what is striking about this task is that we can again see the similar generalization, a kind of length generalization at the test time. You can train the model on the points, 7 points. So x7, you basically transport 7 points to 7 points. And you can test it on 8 points. So you can change the number of points, the distribution completely change, the distribution of the input completely change. But still the model can approximate the optimum solution quite well. Not perfectly, but it's quite decent. So one more interesting fact that is emerging is that if you plot the intermediate data representation across the layers, you will see that the kind of data the model is iteratively solving this task. So if the solution is this, you converge to the solution across the layers iteratively. So this is not imposed by the optimization that you use. For you, eventually the last layer matters. But what this kind of showing is that the model is doing, again, iterative optimization to solve this task. So what we can do is that we can show that there is a transformer with fixed parameters at the test time that can solve OT for any input size up to error that vanish with the number of layers that transformer has. So, and the reason is that they iteratively solve this task across the layers. So just to show you, one of the implications of this result is sorting. So sorting is particular optimal transport. So if you prompt this transformer and model that I constructed for the proof, and you prompt it like this, it can sort with some error. What does this mean by error? So it's not doing merge sort or quick sort or something that we do. It does something different. So it's basically, for example, it can change the element value. So if there is a 0, it can generate 0.01, which is not exactly 0, but approximate the 0. So they do sorting, language model do sorting in different way, using continuous optimization, not the kind of discrete optimization that we use. So, okay, so I have other part of the talk about the mechanism of optimal transport, but I want to pause here for questions because it's good to, before going through more technical topic, I want to see whether there are questions about the statement of the result.
So may I have one? If you go back actually to the previous slide, isn't it a bit, no, the one actually before, and the one, no, sorry, the one with the bound on the error for the optimal transform.
Oh, the bound with the bound, okay, sorry, yes.
Can you recall N was, can you recall the definition?
Yes, N is the number of points that you provide in the test time, the number of, let's say,
yes, okay.
the number of xi and yj that you have. They are N, and the size of parameters that you want to estimate is N. You want to predict N, estimate a solution of the matrix operation of size N.
Isn't it a bit, let's say, worrying as a result to see that the error for such, one can argue that it's a rather simple problem compared to the tasks transformers are faced with, that the error scales so badly with the number of layers. I mean, I do not expect, I mean, you would need a very large number of layers for these bounds to be small somehow for such a simple task. So isn't it a bit, is the bound, do you expect it to be very loose or
Yes, this is very good question. I think the bound is very loose because it's initial bound on the solving task. So there is no other result that provides the bound. So there is no research to optimize this bound. But as you said, I expected to, I will not surprised to get a kind of bound independent of the N even. The reason is that suppose that if you so that the magic of the gradient descent optimization for convex is that its dimension, its convergence is dimension independent, and when you increase the N, the dimensionality is changing. So, but I was not careful in the proof to optimize it with respect to N. For me, the most important factor was that you can improve the bound with the number of layers. And even the square root of the number of layers is sounds to be very loose bound, because I think, in practice with, I don't know, 20 bounds transformer, with 20 layers, the transformer can provide good estimate, but I need a lot of layers for the proof. So this bound is not fully optimized. I don't know what is lower bound, what is upper bound, and so on. But thanks a lot for asking.
Thanks for the clarification. I don't see any other questions. I think you can continue.
Okay, thanks a lot. So the question is that how transformers solve the Wunsch problem. And the answer is that, so we talk about the attention layer. It is a kind of gradient of a convex function. So how it connects to the gradient of a convex function. And so the first question, maybe they do a kind of convex optimization. So we know from long time ago that this integer program admits a linear program kind of expression. And we know that if you optimize instead of over the set of permutation matrices or over the set of doubly stochastic matrices, you get the same solution. Why is this case? Because of the fundamental theorem of linear program that state the solution of the linear program over the polytope are among these extreme points. And the extreme points of doubly stochastic matrices or permutation matrices. Okay, so this is kind of background. Do the language model can solve this kind of control-wish problem, linear program of optimal transport? I couldn't prove it, so I needed to go one step ahead and consider a kind of different formulation, approximate formulation of optimal transport proposed by Marco Kotori, that, you know, they have optimal trans is regularization minus entropy regularization for optimal transport. And in this formulation, the magic is that if you write a dual formulation, you can significantly reduce the number of parameters from n squared to n. But I didn't use it for this purpose. The reason that I was in favor of this formulation was that the attention layer can optimize the kind of gradient descent method on this objective. And they can, you know, using that, they can solve, they can iteratively solve entropy regularization OT. So the other fact I need to stress is that, you know, with changing the regularization, you can control the kind of approximation factor that you have. So the whole idea of the proof is that you can implement the gradient descent of this function iteratively, not gradient descent, the gradient descent times some diagonal matrix, what we call it adaptive step size gradient descent. You have different step size for each coordinate. Can we use the same step size? I don't know. So it was difficult for me to find one kind of choice of a step size that gives us convergence proof. So basically, this choice of a step size can be tuned by the parameters of attention, and I choose it such that you can get the rate. The rate is very slow, by the way. So just a little bit about how we can prove transformer can implement gradient descent. So what you can do, you can put all the data you have in the hidden data representation matrix and plus some additional kind of component you need, some bunch of zeros and ones, and also the gradient iterate. And then, you know, when you pass this matrix through two attention head and combine them, you can get one step of gradient descent. So you can go one step forward here. And one important factor is the important observation is that for the proof, I needed to engineer the prompt. I needed to plant a lot of one and zeros in the input and provide additional kind of memory where the attention can read and write the gradient iteration here. And this problem engineering was actually important in practice. If you just remove it even for one dimensional case, I didn't observe a good performance for optimal transport. So thank you so much for your attention. I will conclude here is that so at the test time inference, at the test time computing language model, we only have some matrix operation imposed by attention layer. It seems to be simple, but it is incredibly powerful. and it can implement various optimization methods. So I talk about 3 different tasks that you can solve with the optimization and with this matrix operation, linear regression, optimal transport. And if you want to know more about it, there is a recent result of us about reinforcement learning. So thank you so much for your attention. And I thank my co-authors and collaborators on this project. Please go ahead. I'd be more than glad to answer the question that you
Thank you
may
very
have.
much. So are there questions that were not asked yet? All right. I don't see any. I think your poses were efficient and everything was asked already. So if there are no further questions, let's ask the speaker again.
Okay, thank you. Thanks, Anna.
Thank you very much for being there.